Okay, this is 2024 for response question number 6. So hopefully by now you've taken a look at and read over the question stem and made an attempt to try and complete this problem. So now I'm going to walk through each part. So the first question here is telling me to determine whether the Maclaurin series for f converges or diverges at x equals 6. So when looking at our series right away here, we're going to plug in, I'm going to take that same series up there and I'm going to plug 6 in so that we can see what ends up maybe canceling or being simplified in this situation. And so when I plug 6 in for x, again there's x, what we can see is that the geometric terms are going to cancel out, leaving me with just this series right here. So it would be n plus 1 over n squared. Now, in terms of using all of our series tests, there's nothing that is similar to, or I'm sorry, I should repeat, there's nothing that's exactly the same as, but it is similar to the harmonic series. And again, the reason I'm making that decision is I'm looking at the n over the n squared, and so relative power-wise, this is similar to the harmonic series 1 over n. So this is a great place for me to use the limit comparison test. So we're going to take the limit as n approaches infinity of n plus 1 over n squared, divide it by 1 over n, but really I'm going to multiply it by n over 1 in that situation. And so when I simplify that, I'll even distribute that into the problem here. We get the limit as n approaches infinity of n squared plus n over n squared. That limit is equal to 1. And since that is finite and positive, remember that this diverges, so that means that the series we're working with here is going to diverge by limit comparison with our harmonic series. Now you can say with harmonic series like I did, or you can simply write the set notation of this 1 over n. Either or takes care of that for part A. Okay, let's look at part B, which is going to be using some sort of error. Now the question here when we read this right away is, are we using the alternating series error bound, or are we using the Lagrange? Let's see if I can spell that correctly. We're using Lagrange here. Right away, we always want to make a decision here based on what we see with the series. If it is an alternating series, then we're going to want to use the alternating series test in terms of the error bound. And that in negative 1/2 inside of the n is an alternating term. So that's what I want to do. Now we do want to acknowledge this somewhere in our work in order to make sure the reader knows that that's the test we're actually using. So I'm going to say something on the lines of, since f of negative 3 is an alternating series, which is what it has here, then we can use the alternating series error bound. And so what does that end up telling me to use? Well, it means that the error is going to be less than or equal to the next term in the series. So in this case, since we're trying to show S sub 3, the third summation, we're going to look at the fourth term. So our a sub 4 term in this case would be, if we plug in 4 into this, we would get 5 in the numerator, and then we would get 4 squared or 16 in the denominator, and then the alternating term would be negative 1/2 raised to the 4th power. So that means my error is going to be less than or equal to that, not equal, less than or equal. So make sure you keep that in mind. 5/16 times, that would now become 1 over 16. That equals 5 over 256. Now we are trying to ensure that this is less than 1 over 50. I am sure that this is going to be indeed less than 1 over 50. And so as long as I'm acknowledging that I know that this is true, we don't have to prove it. You just have to believe it to be true. And as long as that's the case, we are good to go here for part B. Okay, let's move on to part C. In part C, it is asking us to find the general term for the Maclaurin series for f prime, the derivative of f, and then it asks us to find the radius of convergence, for the Maclaurin series for f prime. Okay, so if we're taking the derivative, right, we're taking f prime, we're taking the derivative of this. Now, what we have to remember is that everything here is a numeric term except the x to the n. So really all I need to focus on here for part C is taking the derivative of x to the n, and the derivative of that using the power rule would be nx to the n minus 1. Everything else is just a coefficient. So that's what I'm going to start by writing here for part C. So f prime is going to be equal to n equals 1 to infinity. I'm literally going to write the n plus 1 as the same. I am going to write the n squared and the 6 to the n all as the same. The only part that's new is now I'm going to multiply it by n times x raised to the n minus 1. And so what I've created here is now that derivative. And if we want to simplify said derivative, we can also do that as well. So in this case, the n and the n squared will cancel a term out. So we would get n plus 1 x to the n minus 1 over n times 6 to the n. So we have our series now. That takes care of what f prime is equal to. But now the question is, what is the radius of convergence? Now, this can be done very quickly or very timely. So time consuming, I guess, is what I probably should have said there. So notice that right away in the question in the beginning told you that f has a radius of convergence of 6. So when you take the derivative of a series like we just did here, the radius of convergence does not change. And so this question is really testing you on whether you know that fact or not. And so I can actually go straight to my conclusion and say, since f has a radius of convergence of 6, you have to state that, it follows that f prime has a radius of convergence of 6. Now, if you didn't know that, and you didn't know that fact, what would plan B be? So I'm going to write this as plan A. Plan B would be you would have to do the ratio test for f prime, meaning you would have to take this term and perform the ratio test for it. Now, the good news is if you do that, you will absolutely get the radius of convergence of 6, but we don't want to do that because that is very time consuming. So if you ended up doing that, you can still get all points for doing that and get all the correct points for that problem, but just note that you may have sacrificed some time doing that. Okay, we're going to get down to part D. Now, the reason I didn't do it in part C was because I'm going to end up doing the radius of convergence in part D anyway, so you're going to get to see me walk through one here because we have a brand new series, g of x, given as this, and we are going to indeed use the ratio test to determine the radius of convergence. So right away, let's go ahead and set this up. So this is going to be the limit as n approaches infinity of the absolute value of. Now we're going to go into each individual term and put in n plus 1. So n plus 1 is already in the first, so that would actually become n plus 2 times x to the, now I would write this as 2 times the quantity n plus 1. Now I'll simplify all that out in just a minute. And then over n plus 1 quantity squared, and then 3 raised to the n plus 1. We're going to times it by the reciprocal of exactly what you see up there. So n squared, 3 to the n, over n plus 1, and then x to the 2n. Now we know that this needs to be less than 1 in order for me to have a radius of convergence, so we're going to go ahead and put that there ahead of time. All right, where do we go from here? So we need to clean some of this stuff up. So I am going to just simply write this as 3 to the n times 3 to the first. And now this, we got to be careful. This is really 2n plus 2. So actually this is x to the 2n times x squared. So when we have all that stuff now, here's some things that are going to cancel. 3 to the n's are going to cancel, and then our x to the 2n's are going to cancel. And so what are we left with? Well, all of the n terms, let me gather them together because that's going to be part of my limit, and that can also get removed from the absolute value because those are always positive terms. So we would have n plus 2 times n squared over, and then the denominator, we still have this 3. This 3 often gets forgotten, so you don't want to forget that. Then we have n plus 1 quantity squared times another n plus 1. And so the only thing left inside of the absolute value is actually going to be this lonely x squared here, and that's still indeed going to be less than 1. Okay, we're almost done. This limit here, we have to look at our relative powers here. So it looks like in the numerator, the relative power is n to the third power, and also in the denominator, it's n to the third power, but there is this coefficient of 3. So when I take the limit as n approaches infinity, this is going to equal 1/3 times the absolute value of x squared less than 1. Remember, to have a radius of convergence, you need to have your absolute value of x minus c be less than, and that's going to be your r. So we need to keep that in mind as we're doing this. So I can multiply both sides by 3 to get this answer, but because of this x squared, we're going to have to deal with this to get x by itself, just like this form is asking us to. So I'm going to remove the absolute value bars. I can because of the x squared, take the square root of both sides, and then we're going to end up with here as x is less than the square root of 3. That root 3 right there is my radius of convergence. So the radius of convergence here is the square root of 3. And that will conclude 2024 question 6.